Hello, ladies and gentlemen, and welcome to Mr. Saucedo's YouTube videos. Today we're going to be talking about entropy and Gibbs free energy. So let's talk about entropy. So entropy is abbreviated as a capital S, and it is a measurement of the amount of disorder and randomness in a system. So we've already talked about the first law of thermodynamics, and we talked about how it represented kind of a equivalency of energy, right? So now the second law of thermodynamics is all about entropy, and what it says is that in an isolated system, which means that heat is not being exchanged if it's isolated, natural processes are spontaneous, meaning they happen without any input, when they lead to an overall increase in the amount of entropy. So in other words, all reactions in nature in the universe tend towards disorder. That doesn't mean that order doesn't exist. Obviously it does. That just means that the tendency is that spontaneous things become more and more disordered over time. So the best example of that is involving playing cards. So let's say that I give you a pack of playing cards and I say, okay, shuffle it a certain number of times. What are the odds of you shuffling them and then all of a sudden them being in numerical order? Ace, through king, each suit following the next. The odds of that happening are almost nothing. Instead, what normally happens is the deck gets more and more and more mixed up. So the way that we can think about this are that if we are playing poker, so 5-card poker is a simple type of poker and easy to keep track of all of the cards. So let's say I give you a deck, we play poker, we each take 5 cards. There are 2,598,960 different hands that you could be dealt that are, again, unique from one another, right? All of them are spontaneous, assuming that we shuffled the cards well enough, okay? And so most of the time, what you get is a disordered hand. The odds of you getting a ordered hand are very slim, but they're not impossible. Otherwise, again, poker wouldn't be a thing. So here are your odds, and there's a way of measuring it. So a guy named Boltzmann found this relationship between entropy and just nature. And so it's actually engraved on his tombstone, but it's S equals K ln of W. Now, you don't really need to know what these things mean, but K is a constant, obviously, right? Anytime we see Ks, we just think of constants. But K is a constant that's related to the ideal gas constant, the universal gas constant, and W is kind of a way of representing the amount of different states of disorder, often called microstates, that exist within a system. Ln is the natural log. So here are your equivalencies if you were just randomly dealt 5 cards from a deck. So overwhelmingly, the odds are that you're not going to have anything, that you're not going to have a pair. But having a pair is almost about as likely, let's say, as not having a pair, okay? So they're pretty close. Having 2 pairs, even less likely. Having a 3 of a kind or a straight or a flush or a full house or a 4 of a kind or a straight flush. Having a royal flush, there are only 4 ways for you to get a royal flush in poker out of a possible 2,598,960 possible hands from a single deck. Now, if we add in a second or a third or a fourth deck, these numbers get even more ridiculously small. But notice that if we take the natural log of these odds, that we get sort of like a good idea of a graphical way of thinking about this. So another kind of mind trick when we're thinking about entropy that I found online, so I'm not entirely sure if it's true, but it's a pretty good example, is what are the odds of, if you were in an average-sized living room, of all of the air molecules in the room moving to the corner of one of the little corners in your room? What are the odds of that happening? So obviously you'd say they're basically 0, right? And it would be kind of the same as saying, what are the odds of you being dealt a royal flush? Basically 0. Not impossible, though. And so all that entropy is talking about is how many different possibilities are there and whether or not we can quantify that. And so what are the odds of all the air molecules going to the corner of your room? Well, it's not very likely. This represents those odds. 1 to the power, so 1 over, okay, 10 to the power 10 to the power 27. So that is so ridiculously small that it's basically impossible, but it could happen. Entropy is just, again, one of those concepts that's a little bit harder to wrap your head around. So there's another good example of that. So what do we need to actually be able to do? So if you are looking at the change in entropy of a system, if that is going to be greater than 0, that means that your reaction is becoming more disordered. So remember, entropy is inevitable for the most part. So if it is a positive value, then it is going to tend towards disorder. Now, on the other hand, after you do your change in entropy, what are the odds of it becoming more ordered, right? That would mean that if you're getting a negative number, if you're getting a negative sign when you do your change in entropy. So in general, though, gases are more disordered than liquids, and liquids are more disordered than solids. And again, that makes sense, right? If I have a cube of ice, there are less possible states for it to be in. There are very few microstates for it to exist in because the water molecules are all stuck in one location. Whereas in a liquid, they are more free to move, meaning there are more states possible. If you're in a gas, you can go anywhere within your container. So now again, we are increasing the amount of randomness, the amount of microstates, and normally that just kind of makes intuitive sense to most people. Now, also, if a process is increasing the number of particles, that means the system will be more disordered. In other words, if I take a giant block of something and I break it into pieces, that means that the original block was more ordered than the block being broken apart into hundreds or millions of pieces. Again, that makes sense because that is entropy. So, what is the unit of entropy? The unit of entropy is normally measured in joules per degree Kelvin per mole. So joules over Kelvin moles. A lot of times the mole is removed, and so because we're dealing with balanced equations and stuff, and everything tends to work towards balancing equations in this class, right? Sometimes it's just measured in joules per Kelvin. Now, here are just a couple of situations, and it asks you, do you think that entropy is increasing or decreasing in this system? So let's take a look at the first one. We have nitrogen gas and hydrogen gas reacting to make 2 ammonia gas molecules. So just picture in your head what would be happening. Is that increasing in order, increasing in disorder? How is that happening? So entropy would be decreasing. We are creating more order. We have 4 particles of gas on this side. We only have 2 particles on this side. What about this? I have liquid water changing into gas, so steam. That would be increasing disorder, so I would have an increase in entropy. What about this? I have calcium carbonate as a solid, and I am breaking it into calcium oxide and then CO2 gas. Again, it's increasing, right? I have a gas being made, and it's being broken into 2 parts, which lets me know that's happening. Here I have ammonium nitrate, and I have water, and I am basically just making a solution of ammonium ions, and I'm making some nitrate ions. Again, take a guess. So again, it's increasing. I have a solid and a liquid, and then I have aqueous solutions. So by putting the solid in the liquid, I am now creating a situation where I now have ammonium ions floating around in solution and nitrate ions floating around in solution. They are more disordered than they were here.